Hello dear students, in today's class, let us learn about the theory of plane transmission grating. So this is a special instance where we will see the diffraction phenomenon. Now here, let us see what is actually happening. Here the light waves are coming from infinite distance. Parallel beam is falling onto the diffraction grating, and hence this is a kind of Fraunhofer diffraction. Now, what is a transmission grating? Normally, this is a grating that we use in our labs. And this kind of setup consists of alternate opaque and transparent lines. So within this, there are small opaque lines followed by a small transparent line. And after that, again an opaque line, then a transparent line, and so on. There are fine opaque and transparent lines that is engraved onto this grating surface. So as we know, opaque surface will not transmit light and transparent surface will transmit light. So as a result, this can be considered to be an plane transmission grating. Here, this is the opaque section. After that, we have a transparent section, then again an opaque region, then again a transparent region, and so on. So this is a diffraction grating, a cross section of diffraction grating taken in a specific manner. Now when light falls onto this diffraction grating, the transparent sides, the transparent sections will pass the light waves and the opaque sections will block the light waves. Now depending on various interference conditions, different patterns will form onto the screen, on the screen here. So since these light waves has to be focused, we put a lens here. So this lens will focus the light onto this screen over here, this focal plane. At the focal plane, this lens will focus light, and here on this screen, we will get a pattern. Now let us consider whether this pattern will be constructive or destructive at various points. For that, we will have to consider how the waves actually interfere, how the different waves coming from different points interfere, whether they are interfering constructively or destructively. And we will think about all that in order to find whether a particular point P will be bright or dark. So here you can see light waves that are transmitted through different points. Now consider two specific light waves coming from the first two slits. So the first wave is coming from the top part of the first slit, and the second wave that we consider is generated from the top part of the bottom slit. Now what is the separation between these two? We assume that the width of the transmitting region, the transparent region, is A, and the width of the opaque region is B, the length or the width. So what is the total length of one transparent region and one opaque region? It will be A plus B. So we have the plane transmission grating with opaque regions followed by transparent regions. The width of the transparent region is A and the width of the opaque region is B, so that width of one transparent plus one opaque region will be A plus B. We are considering light wave forming at the top part of the first transparent region and the top part of the second transparent region. So what will be the distance between them? It will be A plus B. So here we consider light wave coming from the top of first transparent region and the top part of the second transparent region. So here their spatial separation will be A plus B. Now these waves will follow this path, then after falling onto the lens, they will be focused. So that they can actually follow any path. From there, in fact, wavelets are being produced. And depending on various positions on the screen, they will meet up constructively or destructively. Now, in order to find the condition for the constructive interference or destructive interference of this consecutive wavelets, what we will have to think is the concept of path difference. What is the difference in path traversed by these two wavelets while reaching a particular point, an arbitrary point P? So let us think about that. Let us derive an equation for the path difference between two wavelets, two successive wavelets produced by two consecutive or two adjacent transparent regions. Now, in order to find the path difference, the normal method that we follow is to draw a perpendicular. So this is another picture. Here we can see in more detailed manner. This is the opaque region, the transparent region, its width is A. Then this is the opaque region, its width is B. Now they are traversing a particular path. They are being focused by a lens onto a point P. We are checking what is the path difference between the light waves produced from A and produced from this point and this point on reaching P. For that, the normal method that we use is to draw a line, draw a perpendicular line from the first point to the second ray. Consider a perpendicular line. Now, this region before the perpendicular line is the extra path traveled by the ray 2. So this is ray 1 and this is ray 2. From the perpendicular line onwards, the ray 1 and the ray 2 travels the same distance. This moves like this goes like this, and after that they travel the same path. So the path difference is the extra path traveled by the ray 2 that lies ahead of this perpendicular line. So let us formulate an equation for this extra path traveled by the ray 2. What is this length traveled by ray 2? Now for that we consider a right triangle given by these points. Suppose this is A, this point is say M and this is C. Consider the right triangle AMC. And suppose this angle at which the point P is seen, suppose that is theta. So here we have this angle is theta. What is theta angle? Theta is the angle between the center line connecting the midpoint and the angle at which the point P is observed. So from here, at what angle the lens is to be bent or the point of view should be turned to observe P. This angle is theta. Now if this angle is theta, then you can calculate this angle, angle CAM will also be theta. How does that come? We have angle MCN is equal to theta. Angle MCN is theta, this angle is theta. Therefore, angle BCM will be 90 minus theta. And automatically, since this is a right triangle, this angle is 90 degree. Angle CAM will be theta. So angle MCN is assumed to be theta, then automatically angle CAM will be theta. Now if that is theta, for that right triangle, we can write an equation for CM. CM is the opposite side. So CM divided by the hypotenuse, which is AC, is equal to sine theta. This angle is theta. So sine theta is equal to the opposite side CM divided by the hypotenuse, which is AC. Now AC is the length A plus B, right? So CM is equal to, CM divided by A plus B is equal to sine theta. Or I can write CM to be equal to A plus B sine theta. Now what is CM? CM is the path difference between ray 1 and 2. Now we have the path difference equation. So I can write in our usual notation, we write delta is equal to A plus B into sine theta. Now what is the condition for constructive interference? For constructive interference, path difference should be an integral multiple of lambda. Delta should be m lambda for constructive interference. So equating these two, I get a plus b sine theta is equal to m lambda. So this is the condition for the point P to be bright. So at points where, at angles where this condition is satisfied, we will have a bright point. So maybe at Q and so on. If theta is equal to 0, then this condition will be satisfied. So the center point will be bright. After that, at certain angles where this condition is satisfied, we will have bright points. Now what are A and B? A plus B is the width of the transparent region of the grating. B is the width of the opaque region of the grating. Now we have a relation n will be equal to 1 by A plus B. N is the number of lines per unit length. So A plus B is the distance in which you can find one line, right? One opaque line. So 1 by A plus B will give you the number of lines per unit length. Now, applying this equation, we can write sine theta divided by n equal to m lambda, or sine theta equal to n m lambda. So this can also be stated as the rule or the equation for the plane transmission grating for us to have a bright point. So if we look at the intensity pattern, intensity distribution, you can see that there are some maximas at which constructive interference is happening. In between, we have regions of minimum intensity. The center will be maximum because at that point, if you substitute theta is equal to 0, m equal to 0, it implies that the center point will be bright. Center is bright. So this is the principle of plane transmission grating. These are the equations that comes to play in a plane transmission grating. I hope it is clear for you. Thank you.